Good day, everyone. Our first topic for today is all about the DC transformer model. And later, I will explain the concept of transformer modeling in DC to DC converter. So here, we have a power input equals to Ig times Vg, which is the input voltage and the input current. And we have a power output which equals to IV, and the D in the middle is our control parameter, which is the control input that decide what will be the output voltage. So the basic equation of an ideal DC to DC converter, the P input is equal to P out, or the output power. So VGIG, which is the input voltage and input current, is equal to VI. So when we write it in terms of transfer function, we can write it as V is equal to M times D times Vg. And in terms of current, similarly, Ig is equal to M times D times I. So this is the comparison of DC to DC converters in terms of output voltage, duty cycle, peak-to-peak ripple current through inductor, peak-to-peak ripple voltage through the capacitor, critical value of the inductor, and the critical value of the capacitor. So these formulas are important to solve our DC to DC converter problems. The DC transformer model of the DC to DC converter models the basic properties of ideal DC to DC converter because we assume that power input is equal to power output. So conversion of DC voltage and currents are ideally with 100% efficiency. Conversion ratio M controllable via duty cycle D. So the solid black line in the middle denotes ideal transformer model. So it is capable of passing DC voltages and currents. The time invariant model, or the no switching, which can be solved to find the DC components of converter waveforms. So here in the next slide, we have an example. A DC to DC converter are used over here, and the load resistance is R, the output voltage is B, and the current that will flow to the load is I. Input voltage is Vg, current Ig, and R1 is representing the source resistance. This is the control parameter of our converter circuits. When we analyze the circuit, the first step is to replace this converter with its equivalent transformer model. Its equivalent transformer model is this, and its ratio is 1 ratio of M of T. So we are going to replace this converter with a transformer model, and we are going to push these sources into the transformer. So when we push the sources into the transformer, it will be multiplied by the square of the ratio. That is M of D in this case. So when we push the source into the transformer side, it will be modified. When this voltage is moved into this other side, will be equal to M of D into VL. So it will be modified into factor M of D. And similarly, when we push the resistance R1 to the other side, it will be modified into this factor M squared D. So now we are going to find the output voltage and use the voltage divider rule, R over R plus M squared D into R1 times the voltage that you are going to apply, that is M of D times V1. So it will be resulted into this equation. So once you convert your DC to DC converter into the transformer model, you can use all the basic concept of the transformer model to simplify the converter circuits. So our next topic is switch realization. So first we will discuss the realization of switches and power converter using semiconductor devices such as power transmitter and diodes. So there are two major topics that we're going to discuss. The first is when we have an ideal switch, how do we decide whether we replace it with a transistor, a diode, or something else in order to make it work in the power converter application? And I'm going to introduce in this lecture the idea of single quadrant, 2 and 4 quadrant switches and how to decide which one of these is we're going to use depending on the application. So, semiconductor devices are a single pole, single throw devices. They have two power terminals and a transistor or a diode that acts as a single pole, single throw switch. So here we have a buck converter with one single pole double throw switch. The switch will on and off over time that move whether on the position 1 or in position 2. So we replace the single pole double throw switch with these two single pole single throw switch, and we can realize each of the single poles single throw switch with a semiconductor power device. A single pole double throw switch have only two possible position, whereas the two single pole single throw switch we have two more cases. The switch can be in position 1 or in position 2. If the switch A is off, the switch B is on. If the switch A is on, the switch B is off. So we can't enable both of the switches at once because it can destroy the converter. If we short out the power source, we can have a very large amount of current flowing around the loop. So the other case, when both switches are off, it can happen and it can completely change the characteristic of the converter. We also need to talk about switches with respect how many quadrants of operation they have to work with. So here we have a single quadrant switch example. The horizontal axis is the offset voltage imposed on the switch by the converter when the switch is turned off. So we also call this the blocking voltage, or how much voltage does the switch have to block when it's off. So the off-state voltage generally determined or given by the input voltage Vg, or perhaps the capacitor voltage in the converter. Likewise, the switch on state current is the current imposed on the switch. Generally, the on-state current is an inductor current or some combination inductor currents. And this can be the function of duty cycle. Also, it's a function of the load current. So again, we have to see what is the on-state current and how does it vary with a duty cycle. Or can it be positive sometimes or negative? So let's begin here. When both of the off-state voltage and on-state current are lying on the positive, and so this is the first quadrant of this plane, and we call this the single quadrant switch for this particular example. Okay, there are many possibilities in this different application that may require one or more of these. So in the single quadrant switch that I mentioned earlier is one of the example, and in fact which quadrant does it have to operate. So there are four possible quadrants in this single quadrant switch. The next case here is called the current bidirectional 2 quadrant switch, where the switch must conduct both of the positive and negative current. So perhaps one duty cycle the current is positive and the other is negative, but it only has to block positive voltage when it's off. As so, we can call this current bidirectional 2 quadrant switch. There are two possibilities here depending whether the blocking voltage is positive or negative. The third example is the voltage bidirectional 2 quadrant switch. in which its switch has to block both polarities of the voltage when it's off and only conduct one polarity of a current. And finally, we have the 4-quadrant switch, the most general case where the switch may have to do anything. It can block either positive or negative voltage when it's turned off, and it can conduct either positive or negative current when it's turned on. So let's move to power transistors such as the bipolar junction transistor and the newer isolated gate bipolar junction transistor. BGT and IGBT are an active switch controlled by terminal C. So both are single quadrant switch that can conduct positive current when switch is on and can block positive voltage when switch is off. So provided that the intended on state and off state operating points lie on the transistor I and V characteristic, then switch can be realized using BGT or IGBT. So here's an example of buck converter. Let's illustrate by example how to go to analysis of two switches to decide how they must be realized with transistor and diode. So here we have the switch A and switch B and arbitrarily defined voltages across the switches. So VA, we define the reference direction as positive and to negative, and BV is from negative to positive. And now we have to do is to figure out what is the state voltage or the on state current imposed in the switch by the converter, and also what is the off state voltage that the switches have to block. So let the switch A first. So when the switch is on, we have A is on and B is off. Then you can see the current that the switch A conduct is an inductor current. So IE equals to IL. Now we know that the inductor current is also the load current. So we have inductor current IL equals to V over R, which is the load current, and V is D times Vg. So we have dVg over R. And it is the current that the switch has to conduct. Now all of this is all positive quantities. Now we assume that term B is all positive. So D is positive, Vg is positive, and it have a positive load R. So R is also positive. So that the on state current is positive. So here is the on state current IA. It's a positive current. When A is off, what voltage does it have to block? But when we turn A off, B is on. The voltage is equal to Vg. And that's the positive quantity. So when the switch is off, it blocks a voltage Vg, so that the on state current and the off state voltage are both positive in quadrant 1. And therefore, we can realize the switch with a transistor. Say an IGBT. When an IGBT, we can block positive voltage and positive current, that which is how it designed to operate. So let's consider switch B next. So when switch B is turned on, switch A is turned off, what current does it conduct? So with switch B on and switch A is off, we can see that IB is equal to IL, and the defined polarities of IB and IL are the same at this case, and so the positive quantity. And we're conducting positive current when switch B is off, then we have switch A turned on, and it has to block VG. But be careful when we define the direction. Voltage V is actually negative VG, which is a negative quantity, so we have to block the negative voltage. So in this case, we have a positive current on state current, a negative off state voltage when a second quadrant, and that's a diode. So we have to draw current IB, VB, positive, negative. So switch B must be realized with a diode. Now you can see here also that the choice of the switch isn't arbitrary. It could be a diode or a switch on switch A or a transistor at switch B. At least not an IGBT or a BGT. So we have to realize these switches correctly. So by doing the symbol exercise, we can follow in a systematic way to see exactly how to realize the devices. So in summary, we have to put BGT for switch A and a diode for switch B. So that's all for today. Thank you for listening. Have a good day.